Welcome to the Explainer. Today, we're taking what usually feels like some incredibly dense textbook math and turning it into a vibrant visual story. I mean, if you've ever stared at a page full of sines and cosines and thought, okay, but how does this actually relate to the real world? Well, you are exactly in the right place. We are going to completely decode the beautiful language of trigonometry. I actually want to kick things off with this quote from the beginning of the chapter, mostly just because it's brilliantly funny. It says, "A mathematician knows how to solve a problem. He cannot solve it." Right? It's a great reminder that higher level math isn't just about mindlessly grinding out numbers on a calculator. It's really about understanding the deep underlying patterns of the universe. So, honestly, let go of any of that lingering math anxiety you might have, because today is all about the concepts. Okay, let's dive into this. Here's our roadmap for the chapter. We're going to hit the origins of trigonometry, measuring the spin, the unit circle, navigating the quadrants, and finally, the power of identities. First up, Section 1, the origins of trigonometry, where it all began. So, why was this even invented? Well, the word itself actually gives us our first big clue. Trigonometry comes straight from the Greek words trigon and metron, which literally translates to measuring the sides of a triangle. Back in the day, this wasn't abstract at all. It was intensely practical. You had sea captains studying it to navigate the open ocean, and surveyors using it to map out vast new lands. How? By solving geometric problems involving, you guessed it, triangles. But here is where it gets fascinating. What started as just a way to measure a patch of dirt has evolved to explain the very fabric of our universe. Today, trig is used for the science of seismology to understand earthquakes. It helps engineers design complex electric circuits. It is literally used to describe the invisible state of an atom, predict the exact height of ocean tides, and even analyze the musical tones in your favorite songs. So yeah, we have moved way beyond simple triangles. Now, what's really interesting about this early heavy lifting is who was actually doing it. You might think it was all the Greeks, right? But the rigorous study of trigonometry as we know it first truly blossomed in ancient India. Brilliant scholars like Aryabhata, way back in the 5th century, along with others like Brahmagupta and Bhaskara, laid the crucial groundwork that eventually made its way to Europe and the rest of the world. And the pure ingenuity of these ancient thinkers was absolutely astounding. Take the Greek mathematician Thales, for example. Without any modern lasers, no measuring tapes, he famously calculated the towering height of a pyramid using nothing but shadows. Seriously. By measuring the shadow cast by the pyramid, and then measuring the shadow of just a simple staff of unknown height, he could compare the ratios of the similar triangles created by the sun's rays. It's just such a perfect, elegant application of proportional geometry. Which brings us to Section 2, measuring the spin, degrees versus radians. As trigonometry evolved beyond static triangles, it became the mathematics of rotation. So how do we actually measure a spin? Well, we basically have two main tools. First, the one we all know, the degree measure. We take a full revolution and slice it into 360 pieces. It's super convenient for large angles, like talking about a rapidly spinning wheel. But then we have the mathematical powerhouse, the radian measure. A radian directly links an angle to the actual physical arc length of a circle. Think of it like this. If you have a circle with a radius of 1, an arc length of exactly 1 unit on the edge of that circle creates an angle of exactly 1 radian at the center. And because of this direct physical relationship, we know the total circumference of a unit circle is 2 times pi. Therefore, 1 complete revolution is exactly 2 pi radians. This single fact right here, this is the bridge that connects pure geometry to the wider world of real numbers. And that bridge leads us directly into Section 3, the unit circle, mapping angles to real numbers. This is arguably the most powerful conceptual tool in the entire chapter. So the crucial point is this: radian measures and real numbers can be considered one and the same. Just imagine taking an infinitely long string that represents the entire real number line, pinning the 0 to the edge of our unit circle, and just wrapping it around. Every single real number on that string is going to touch exactly one specific point, corresponding to a specific radian measure. It completely unifies rotation with the number line. Okay. Here is our grand scaffolding moment. If we take that spinning angle and place the circle on a standard coordinate grid, center at 0, 0, radius of 1, everything changes. The x-coordinate of any point on that circle, that is simply the cosine of the angle. The y-coordinate, That's the sine of the angle. We've literally just redefined sine and cosine. They're no longer just rigid ratios of a triangle's sides, they are fluid functions that track coordinates as they spin infinitely through space. Now that we've unleashed these functions from those little right triangles, let's move to section 4, navigating the quadrants, the grid of positive and negative signs. Let's see how these functions behave as they spin around the entire coordinate plane. This brilliantly illustrates the beautiful predictability of math. Because sine is our y-coordinate and cosine is our x-coordinate, their positive and negative signs just neatly follow the 4 quadrants of the grid. Sine is positive in the top half, negative in the bottom. Cosine is positive on the right, negative on the left. Tangent, which is just sine divided by cosine, naturally follows suit. It creates this absolutely perfect matrix of behavior. But we aren't just memorizing static signs here. We're reading dynamic patterns. Think about how sine behaves. As the angle opens up in the first quadrant, that y-coordinate rises from 0 all the way to its peak of 1. Then in the second quadrant, it falls back down from 1 to 0. It breathes. It rises and falls continuously, exactly like those rolling ocean tides we mentioned earlier. And this beautiful, predictable behavior leads us to our final section, kind of the climax of the chapter. Section 5. The power of identities, generating complex truths from the unit circle. From the simple geometry of the unit circle, we can actually use basic distance formulas to prove sweeping, foundational rules, like the cosine of the sum of 2 angles. Now, don't panic, you don't need to memorize how to solve this right now. What you really should take away from this is the sheer structural beauty of it all. By just tracking distances on our unit circle, we can prove these interconnected truths about how angles combine and relate to one another. Let's see how this builds, because that one simple cosine identity we just talked about, it acts like a mathematical seed. From it, an entire toolkit just cascades downwards. We can derive the tangent of combined angles, and even these wildly complex double and triple angle formulas. We've basically generated a massive, robust toolkit, a rich mathematical language, and it all stems from a line wrapping around a single unit circle. Incredible, right? Which leaves us with this final, truly remarkable thought. How does a mathematical concept, born millennia ago from sailors mapping the stars and ancient scholars measuring the shadows of pyramids in the sand, now serve as the precise language we use to describe the invisible state of a quantum atom? Well, it's because the universe is built on cycles, on rotations, and on patterns. And trigonometry? It's simply the master key to decoding them. Thanks so much for joining me on this explainer. Keep wondering and keep learning.